Okay, students, let's review days 32 to 34. So we'll just go through this quickly so those of you who missed the review can go through it. All right, so day 32 was chemistry. So here's the learning outcomes. We need to be able to determine and predict atomic structure using the periodic table, predict the number and type of bonds it'll make, whether it'll be polar or nonpolar, and how that has to do with electronegativity, which we'll talk about, explain what an isotope is, describe, draw, and identify a covalent bond. Decide whether molecules are hydrophilic or hydrophobic, explain why and how an ionic bond will form, recognize all the macromolecules, and explain the difference chemically of a saturated and unsaturated fats. All right, so on the screen here you can see that this is an ionic bond, right? So ionic bonds are when the electron completely transfers from one atom to another. And then this is showing you energy, right, which we'll talk about actually later. Okay, so let's practice. So I wanted to, if you can, pause this video and answer these questions about nitrogen. So I'll give you a second to pause. Okay, so hopefully if you're looking at nitrogen, you can see a lot. This is on the periodic table. You can tell a lot from what it says here. So if you're going to decide what the atomic number is, what number is that? Well, it happens to be this number here, 7. This also tells you how many protons, right? So the atomic number is the number of protons. We never change the number of protons. If you change the number of protons, you've done alchemy. Okay, so protons are what matters. It'll also actually tell you how many electrons nitrogen has in its ground state. So if we're just talking about nitrogen as the element, it'll have the same number of electrons as protons. Protons having positive charge, electrons having negative charge. And then if we want to know how to figure out neutrons, then we need to look at the atomic weight. So the atomic weight is here, it weighs 14. So if it's got 7 protons and it has to weigh 14, then it has 7 neutrons, because electrons don't weigh anything. And remember, this 0.007 is not the weight of the electrons, but it's the average weight of the isotopes that we find of nitrogen. So one of the learning outcomes is isotopes, and if you remember, an isotope has a different number of neutrons, and I'll show you an example in just a second. And then how do you decide how many bonds it will likely make? Well, if you look at the atomic number, it has 7 electrons. And so we always have 2 in our first shell, so that brings us down to 5. That means in that second shell, that outermost shell, it's going to have 5 electrons. And using the octet rule that we always want to get to 8, then it will likely make 3 bonds, right, to get up to 8. Hopefully that made sense. And so talking about isotopes, these are some common isotopes we see of nitrogen. Nitrogen 14 is the normal one that we most often see, but you can also have nitrogen 15. You saw that when we did the Michelson and Stahl experiment on the DNA replication. They used heavy nitrogen, so it actually has 8 neutrons, and so it weighs 15. And you can even have 9 neutrons, and it'll weigh 16, and it'd be called nitrogen 16. Okay, so let's practice another one. So take a moment, pause this video, see if you can answer these questions. Okay, so same thing here. Atomic number is 17. So what does this tell us? Well, it tells us that it's chlorine. It tells us that it has 17 protons and also that it has 17 electrons in its ground state, so that it's got a total charge of 0. Okay, the atomic weight of 35.5 tells us that it's got not only 17 protons, but then it's got an additional, depending on if you round up or down, if we're going to 35, then it's got 18 neutrons. If we're going to 36, then it has 19 neutrons. And so then to figure out bonds, and let's see if I can actually, I was going to try, I can draw. Okay, so pen color red, sure, okay. So if we're drawing chlorine, remember that in the first shell, it's going to have 2 electrons. I'm going to draw them as X's. Okay, so that's, now we're down to 15 that we have to draw in here. Ooh, in the second shell, it will have 8. So we'll do 2 here, 2 here. Oh my gosh, you guys, this is not ideal. 2 here, and 2 here. I like to draw them in pairs. I really don't care how you draw them, but normally they do hang out in pairs. So now how many do we have? That's 8 and 2, so that's 10. So that means we got to draw another shell, and in that last shell, if we've got to get up to 17, then we have 7 more. So 2, 4, 6, and 7. So you can see in order to be full, it just needs to make one more bond right here to have a full shell. So it's likely to make one bond. All right, I don't know how to get out of my, okay, so it's going to make one bond. Okay, and 18 neutrons is probably a good guess, but again, you can have, oh, my drawing's in the way, you can have isotopes, right? So the chlorine 35 is the normal one, that has 18 neutrons, but you can also have up to 20 neutrons and have chlorine 37, for example. Yeah, so let me see, can I erase, oh wait, hold on, erase pen, okay. So let's move to the next one. Let's try oxygen. So pause the video and see if you can do oxygen. Okay, so again, atomic number is 8, so this tells us that it has 8 protons and 8 electrons in its ground state. Atomic weight says about 16, so 8 protons and 8 neutrons. And if we have 8, then we have 2 in our first shell, which leaves us 6 in our last shell, and to get up to 8, it would likely make 2 bonds. Okay, all right, so oh, and this is showing some isotopes. So there's normal oxygen right here, and then we have an oxygen isotope, oxygen 18, that has 2 extra neutrons. All right, so let's practice. I want you to try to solve this. So do pause the video and see if you can solve this. We've got a hypothetical element called element V. It can make 1 covalent bond with hydrogen, and its most common isotope has 5 more neutrons than protons. Okay, so take a minute and see what you can tell about this. What is the answer? Okay, now I'm going to go through and show you how I would solve this, right? So the big key here is that it makes 1 covalent bond, which means that you want 7 electrons in that outer shell, right? Because then we would get to 8. So let's look at this one. This one's going to have 2 in the first shell, and then 8 in the next shell. That gets us up to 10, and then 8 in the next shell. That gets us up to 18. So it's going to have 2 in its outermost shell. Well, that doesn't work, right? So then let's look at this one. It's got 7, so it's got 2 in its first shell, and then it's got 5 in its outer shell. So it would likely make 3 bonds to get up to 8. So that one's not going to work. This one has 9, so it's got 2 in its first shell. And that leaves 7 in its outer shell. So it would make 1 bond, but let's see if it has 5 more neutrons than protons. So if it has 9 protons and its weight is 23, then it has how many? It has 14 neutrons, which is approximately 5 more neutrons than protons. So this one's looking pretty good. Let's just check this one. 15 in its outer shell, that means it has 2, and then 8, that gets us to 10, and then 5 in its outer shell, so it would make 3 bonds. So this one doesn't work either. Okay, so the answer is C. Then this one says when an electron moves from an energy shell closer to the nucleus to an energy shell farther away from the nucleus, that would mean what? Has it gotten more potential energy or less potential energy? And hopefully you can see that it's going to gain. It's like a spring. If you pull it away from the nucleus, it wants to bounce back, which gives it extra potential energy. Okay, and that's how ATP works, which we'll talk about in a minute. Okay, so let's go here. Recognizing the type of bonds, there's actually a couple things you need to know for this. These bonds, because you can see that they're sharing these electrons here and here, these are definitely covalent bonds. Now the molecule itself, in this situation, we've got these like extra negative electrons out here. So this whole molecule is going to have a negative and positive pole, right? But the bond itself, it would be hard to know whether this bond was polar or not without knowing the electronegativity of this atom and this atom. But in this case, this one looks like it's probably more electronegative. In fact, I know it is. This looks like oxygen. And so these electrons are being pulled this way, and so this would be a polar bond right here. Whereas here, these could be polar. We really don't know, although this looks like carbon, so it's probably not. But the whole molecule itself doesn't really have a pole in any way or the other. Okay, and then here you're seeing that this electron is completely jumping ship, and so this would be ionic. Okay, so this would be polar covalent, this would be a non-polar covalent, and this would be ionic. Okay, so then recognizing types of fatty acids, and so you see here this particular fat, see how the tail is nice and straight and there's no double bonds? This would indicate a saturated fat. This one's got a double bond and this one's got a double bond. How do you know it's double bond? Well, it's 2 lines. And, excuse me, each of these carbons needs to make 4 bonds. And so up here you can see like this carbon right here is making 4 bonds. It's making 1, 2, 3, 4. This carbon here is making 1, 2, and then it must be making 3, 4 right here. So this is a double bond. So this is an unsaturated. It's not completely saturated with hydrogens. This one's also an unsaturated. The only difference here is whether the hydrogens at the double bond are transverse across it or on the same side, called cis. Okay. The difference is that this one, you can see the tail is really bent. So these are going to be liquid at room temperature, whereas if you do a double bond trans, it'll make the tails totally straight. So they'll pack together just like a saturated fat. And so I don't remember if I said this in the video, but we artificially saturate unsaturated fats so that they'll stay solid at room temperature. Like think of grandma's cookies, that frosting, right? We want it to stay solid at room temperature. And so we'll artificially saturate it, and oftentimes in the artificial saturation process we get these trans fats, and our bodies don't know what to do with them, so they're bad. But that's why we do it. Anywho, okay, so that's the fats. Okay, day 33 was water, and we don't have a ton on this. It should be pretty self-explanatory, but we're going to talk about these learning outcomes all have to do with the properties of water and why water behaves the way it does. And water is very unique, and that's what makes life possible on our planet. And so if you look at water, because oxygen is far more electronegative than hydrogen, these electrons are being sucked in this direction. So we get these partially positive charges on the hydrogen ends and very negative feel here on the oxygen side. And so we get these polar bonds. And so as a consequence, water molecules will stick together, right? So another water molecule, its hydrogens that are partially positive, I'm just going to draw a little water molecule here, right? Its partially positive hydrogens are attracted to this negative oxygen right here. And so we get, and this right here is called a hydrogen bond. It's the attraction between different water molecules. So this bond here between this hydrogen and oxygen is not a hydrogen bond. This is a covalent bond. This weak attraction between two different water molecules is a hydrogen bond, and it's what's responsible for all of the properties of water, right? So polarity is because of the uneven sharing. It causes this cohesion. So cohesion means it sticks to itself. So water molecules will stick to each other. Adhesion means it sticks to other things. So because of these partial charges, it can stick to anything else that has a partial charge, like a paper towel, a piece of toilet paper, or a window pane. That's adhesion. Surface tension is due to these hydrogen bonds between water molecules. So you might think this is a weak bond and a weak attraction, but if you land belly flop on a bunch of these, it hurts like heck, okay? And that's that surface tension. And you can actually, I've always wanted to try this, not that I really want to try this, but I'll push someone else off the cliff. But I would always wanted to try putting soap, like dropping soap as you're falling, because soap interrupts these hydrogen bonds, and I wonder if it would hurt less if you went into the water if it was soapy water. Anyway, I'm not going to try that. High specific heat. The reason that the specific heat is the amount of heat required to raise the temperature of the liquid, of the substance, and to raise the temperature of water takes a lot of energy, because not only do you have to get the water molecules moving, but you also have to break all these hydrogen bonds. That's what makes it change temperature so slowly, because we have to break all the hydrogen bonds before it'll start to move and get warm. And same thing with when it cools. It cools a lot slower too, because all these hydrogen bonds have to form. And so this works for evaporative cooling, right? If we're trying to make water evaporate, it takes a tremendous amount of energy, both to make the water molecules vibrate and leave the surface, right, to evaporate. But we have to break all these hydrogen bonds. And so it's pulling that energy both from the environment and from your skin, and it makes your skin feel cool. And then the universal solvent, because of this polarity, it dissolves a lot of things, which is really great. Okay, so then the last day was energy. And so energy, we dealt with enzymes, right? Enzymes lower that energy of activation. This little hump here makes it easier to happen by bringing things together or straining bonds or whatever it needs to do to make the reaction happen more easily. And when you break a bond, and this is, okay, I have to preface this with, I'm simplifying this for biology's sake, but if a chemist heard me say this, they might freak out. And that is when you break a bond, energy comes out. It's not technically true. It's that whatever the new bond that forms when the chemical reaction happens is a lower energy than the other bond, and so energy is released. But all bonds take energy to break, if that makes sense. But because the new bond that's formed, like when you do combustion, the new bond between carbon and oxygen is a lower energy bond than the carbon in the food, and so you get energy released. Okay, so we should be able to calculate the amount of energy released. We'll do that in a minute. Decide whether a reaction is endergonic or exergonic. So anytime it's going down and releasing energy, it is exergonic. Anytime you're putting energy in, it is endergonic. This is the process of energy coupling. Anytime you use an exergonic reaction to drive an endergonic reaction, that's energy coupling. And then we'll predict overall energy loss and gain and describe the purpose of ATP. So in this particular example, it's looking at how we digest our food and then how we move, right? So you take food that has really a whole lot of potential energy. And the reason it has a whole lot of potential energy is because of where the electrons are in the bonds, right? So they're high energy electrons. And when we break those bonds, out comes the energy because the new bonds that it makes are lower energy. A lot of it is lost as your body heat, right? That's what keeps our bodies at 98.6 degrees Fahrenheit. But because the process of digestion and eating doesn't happen in the same place or at the same time as like running a marathon, for instance, we store it temporarily in this molecule called adenosine triphosphate, or ATP, that's pictured right here. And it's simply stored in the potential energy of shoving 3 negatively charged phosphate molecules together. They don't like to be together. And so as you push them together, they have potential energy, like a spring, right? And so we put it in there, and then when we need that energy, we just simply pop off a P, and out comes ADP and P, and a lot of energy. And we can use that energy to drive body motion or whatever we need to do. And I don't know if I talked about this in the video, but you can also break off the second P and make it AMP. So ATP is adenosine triphosphate, ADP adenosine diphosphate, AMP is adenosine monophosphate. There's actually a receptor on your brain for AMP. If AMP starts circulating in your system and attaches to that receptor, it makes you feel tired. It makes you feel like you have to lay down and sleep, because you do. And funny enough, caffeine is a receptor antagonist, so it actually binds to the AMP receptor, so AMP can't bind, and you don't get the message that you're tired, which is why caffeine makes you feel like you're not tired. But what happens when the caffeine wears off, right? That receptor all of a sudden becomes open, and all this AMP that's built up in your system bombards your brain, and then you crash. So anyway, interesting. Okay. So here's the terms you should have learned, right? Exergonic means energy releasing, endergonic, energy absorbing, right? The first law of thermodynamics is that energy cannot be destroyed or created, and so it has to just transfer from one form to another. So it goes from potential to kinetic and back and forth. Energy coupling is what we talked about, I showed you, where you take an exergonic reaction and drive an endergonic reaction. ATP is your adenosine triphosphate. And an enzyme is just a protein that makes reactions easier to happen, lowers that energy of activation. So then this is calculating calories. So just practice for a minute. We kind of did this already before in another unit, but it's the 449 rule. So if you want to pause for a second and see if you can do it, go ahead. And then I'll show you the answer, right? So we're looking at fat. It's got 9 calories per gram, carbs that have 4 calories per gram, proteins that have 4 calories per gram. So you should be able to get to 177, which doesn't match our 170, but that's because some of those, which they're not actually recording, but some of those carbohydrates are probably indigestible. So you're not actually getting calories from them. They're more like fiber. Excuse me. And then let's practice here. So pause this and see if you can put all of these terms onto this diagram. So we're coupling the building of a protein, which is an endergonic reaction, with using ATP, which is an exergonic reaction. So pause the video and see if you can do that. Okay, so The one rule for solving these is always put the exergonic reaction, I'm going to write it right here, on one side. So the exergonic is going to go here, and I'm going to do a cursive because that was a lot easier to write with this dumb mouse pad. Endergonic goes on this side. So we have to decide, okay, building a protein, that's endergonic. So we're going to take our reactants for the protein, our products for the protein. So our amino acids that we're going to use to build it, and then our finished protein is here, which is a PP, a polypeptide, right? And then you have to decide what's the exergonic reaction that's driving that. Well, it's ATP. So we're going to take our ATP and we're going to break it down into our ADP and P. Okay, so we want to separate them. Now remember, this reaction is happening at the same time as this reaction. We're just separating them out so we can see them. And this is your transfer of usable energy. So that should all match up right there. Okay, so if you need to pause and look at that for a second, please do. And then lastly, making ATP, does that require energy or release it? Breaking ATP, does it require energy or release it? So just see if you can answer that. Okay, hopefully this is what you got. Okay, and that's everything for this week. So let me know if you have any questions. Please come to my office hours or any of the TA's office hours. Thanks.